Back in section 5.6, we had some rules for derivatives of inverse trig functions. For example, we had a rule for the derivative of arc sine of x. What was the rule for the derivative of arc sine of x? 1 over the square root of 1 minus x squared. So that yields an integration formula. What's the integral of 1 over 1 minus x squared? It would therefore be arc sine x plus c. Now the formula we're generally going to deal with, we're not just going to have the number 1 there. We might have some other number, so we might have 1 over the square root of, usually it's written as a squared minus x squared. Any idea what you would do to get an integration formula from this, knowing that integration formula up there?
X over a, sine of x over a.
Arc sine of x over a? That's absolutely correct. How'd you get it?
The sines opposite over a functions. And then that one, we assume that one is the, right? No, I don't know. I just remember.
He got the right answer. I'm not sure that his reasoning was correct, but he got the right answer. What you would do, I'm not going to work it all out, but I'll tell you what you would do. What you would do is you would think of this x squared right here as x squared times a squared divided by a squared. And then how does that help? Well, I've got an a squared here and I've got an a squared there. What can I do? Factor out. When I factor the a squared out of there, what am I going to be left with? Just a 1. So we write this way. The integral of 1 over the square root of a squared times 1 minus x over a all squared. This a squared and that square root, they cancel each other out, so that's just an a on bottom. And then in order to use this integration form here, I can't have x over a, so what would I have to do? How do I get it so that I have just a variable there and not variable over a?
That's a to the negative 1.
It is a to the negative 1, that's true. What I was looking for is the thing we always do with integration. U is x over a. So du is 1 over a dx. But don't we have a 1 over a right there? So this becomes the integral of 1 over the square root of 1 minus u squared, which is going to be arc sine of u, but then u was x over a. So this becomes the arc sine of x over a plus c. So that's the integration form we're normally going to use. So I'm going to start a list of new integration formulas for us. So new integration formula number 1, the integral of 1 over the square root of a squared minus x squared dx is arc sine x over a plus c. All right, and then what was the derivative of arc cosine? It was negative 1 over square root of 1 minus x squared. So I could also say this integral of 1 over the square root of a squared minus x squared, instead of using arc cosine, I could use arc cosine, and the only thing I would need is a negative sign. Typically we don't do that. Typically we simply leave this as arc sine. Although you could use negative arc cosine if you prefer. Why do we usually use arc sine instead of negative arc cosine? Now, number 1, we avoid having a minus sign. Number two, which function was easier to work with? Was it easier to work with arc sine or was it easier to work with arc cosine? Arc sine was typically easier to work with. How come? Because of its domain and range. It was typically easier to work with. So that's why we use that in the form of arc sine. All right, and then leave some space in your notes here for formula number 2 and formula number 3. But there's no great surprise on these here. We had a formula for the derivative of arctangent. What was our formula for the derivative of arctangent?
1 over absolute value.
No, this one didn't have the absolute value in it. That was secant.
Oh,
That had the absolute
it's
value.
1 minus x squared. 1 over 1 minus x squared or x minus x squared.
It was plus. It was 1 over 1 plus x squared. Which, of course, we can now reverse. That means the integral of 1 over 1 plus x squared dx is arctan x plus c. But once again, typically we're not just going to have the number 1 there. We're going to have some other number. And so the integration formula that we use is the integral of 1 over a squared plus x squared dx is 1 over a arctan of x over a plus c. And then we have the exact same trick again as we did with our arc sine integration formula. What was the derivative of arctangent? I'm sorry, what was the derivative of arc cotangent? Derivative of arctangent, right there. What was the derivative of arc cotangent?
1 minus x, 1 over 1 minus x squared.
No,
There's this negative.
it was negative 1 over 1 plus x squared. So once again, I could, instead of using arctangent, I could use arc cotangent. But again, the arctangent one had the better domain. So typically we stick with the arctangent function. And then finally, we had a derivative rule for arc secant.
This is more than absolute value.
This was the one with the absolute value. So it was 1 over
Absolute value of x.
absolute value of x.
Square root of 1 minus x squared.
I think it was the other way around. Square root of x squared minus 1. So once again, that leads to an integral formula. The integral of 1 over x square root of x squared minus 1 dx is arc secant absolute value of x plus c. So notice I took the absolute value out of here, but I put it back over there to balance it out. And so our last integration form for this section is the integral of du or dx over x square root of a squared, oh no, I'm sorry, other way around, x squared minus a squared is 1 over a arc secant absolute value x over a plus c. So those are the 3 new forms that we have that we'll use in this section. Questions on any of those?
So we're not worrying about the absolute value of x with the rule.
We bring it back in.
Notice for the derivative rule, we put the absolute value here. For the integration rule, we put the absolute value there. So notice I have absolute value written here. Okay? Alright, so I'm just going to grab some good problems out of the book here.
This chapter is not on the test.
This will not be on your test on Friday, that is correct. This will be on your next test. Integral. Start right with the beginning here. This is number 1. The integral of dx over the square root of 9 minus x squared. Does that fit into one of our patterns? That fits into the arc sine pattern, because the arc sine had a squared minus x squared. So this is arc sine of x over 3. Very good. A lot of people will want to say x over 9. Why is it x over 3? Because this is a squared here in the original formula, but this is a over there. So a squared is 9, which means a is number 3. Number 2. Integral dx over the square root of 1 minus 4x squared. Does that fit into one of our integration patterns? Yes, almost. What do I mean by almost? Our pattern has a squared minus x squared. It doesn't allow for having a 4 right there, does it? So we got to fix that. How do we fix it? Write it as, okay, so this is the integral of dx over the square root of 1 minus 2x whole thing squared. Close. We're going to have to do a u substitution. U is going to be 2x. Because we can have an a squared minus a u squared. We can't have a 2 there still. So if u is 2x, then du is 2dx, which means I need to slip a 2 in right there, which means I need to balance it with a 1/2. So that's what you were missing, Charles. You were missing that 1/2 right there.
Very outside.
Yep.
Should be 1/2 arc sine of 2 over x.
That's right. So we're going to end up with 1/2 integral du over square root of 1 minus u squared. And you're right, that's 1/2 arc sine of u, but u was 2x. So our final answer is 1/2 arc sine of 2x plus c. Questions on that one? All right, how about, we'll just keep going right in order here. Number 3. The integral of 1 over x square root of 9x squared minus 1. I lied, that's not really number 3. Number 3 had 4x squared there, but we just did a 4x squared, so I changed it to a 9x squared just to make it different. It's not really number 3 in the book. Does that fit into one of our patterns? It looks like our arc secant, but again we get the same problem. The arc secant, we have the x out here. We're supposed to have just an x squared in there. Not supposed to have that 9. So what are we going to have to do?
Square the whole thing.
We're going to have to do u substitution. U is going to be 3x. So u is going to be 3x, which means du is 3dx. So I need to slip a 3 in right there, which means I need to balance it with a 1/3. So that's going to be 1/3 integral du over, all right, but I got a problem here. What do I do with this x? Solve. This x is
U thirds.
1/3 u. That's correct. So it's kind of a double substitution type problem that we've seen before. That's a 1/3 u. And then we're going to have square root of u squared minus 1. So something kind of interesting happens. That 1/3 reduces with that 1/3, doesn't it? Because this 1/3 is on the bottom of the fraction, so we would flip and multiply, it would be a 3. Those reduce out, that's kind of nice. This now fits perfectly into our arc secant formula. So this is arc secant of u, but u was 3x. And remember, arc secant gets an absolute value. So that's arc secant absolute value of 3x plus c. Questions on that one?
They won't always cancel out like that with the 1/3.
Yeah, I think they will.
Most of them do cancel
Yeah.
like that.
Yep. When you do that u substitution, I think those will always cancel.
What happens to like the x over a? Because it's just 3x.
Is that because
Or
it's
is
a
it-
one?
A in this case is the number
1.
1, so it's 3x over 1. I didn't bother writing the 1.
But alpha technically be 1 over 1 too, right?
And technically out front it would be 1 over 1 also, correct. But I didn't write that either.
Right.
But you're absolutely right. Okay, let's keep moving here. Number 4. The integral of 12 over 1 plus 9x squared dx. Which form does that look like? That looks like our arctangent form. Except it's the same deal, isn't it? We're not supposed to have a 9 there. So u is once again going to be 3x. U is going to be 3x, which means du is 3 dx. So I need a 3 right there, which means I need a 1/3 right there. But 12 times a third is 4. And then I'm going to have du over 1 plus u squared. So same deal, this time our a is the number 1, so we would have 4 over 1, which I'm just going to write as 4. Our tan of u over 1, u was 3x. Let's see. Questions on that one?
How's 1 over a inside
What was
that?
the example where a is not 1?
We'll do an example where a is not 1, you bet.
Can you go back to the formula for
Yep.
1 over a?
So 1 over a,
The A's, every case we've done, A's been.
In this case, since we had 1 squared, we had 1 plus u squared, a was the number 1.
Well, I had my over the x over a. I had a 1 over a there.
Oh. Alright, so let's do some examples where a is not the number 1. And maybe where they're not so obvious. How about the integral of 1 over x times the square root of 16 minus ln of x and the ln s squared dx. This is similar to number 10, but in number 10 they also had a to be 1, so I changed it to a 16. All right, good ideas. Any good ideas?
U is ln x.
U is ln x. Why is that a good idea?
1 over x.
Because you get this 1 over x down on the bottom, don't you? All right, so there's our good idea. U equals ln x, and then du gives us that 1 over x dx. So this becomes the integral of 1 over the square root of 16 minus u squared du. U equals ln x is always a good idea. Why is u equals ln x always a good idea? What's that?
Get rid of the ln.
You want to get rid of the ln, and why do you want to get rid of the ln? What's the integral of ln? We don't know. That's correct. We will learn, but we don't know yet. So it's always, if you, at this point in your life, if you have an integration problem, and the integration problem has an ln, I promise you that has to be u. It's your only choice. All right, but this one works out well, because this now fits exactly into our arc sine formula. So this would be arc sine of u over 4, because 4 squared is 16. So final answer, arc sine of ln x over 4 plus c. Questions on that one? All right, let's see. How about the integral of sine x divided by 7 plus cosine squared x dx? U is cosine? Just cosine, not the whole bottom? Don't let me talk you out of the right answer. What's that?
Get rid of the 7 then?
Yeah, don't let me talk you out of the right answer. U equals cosine was the right answer. Why? I mean, this is what we typically do. Typically up to this point, when we've had a fraction, we've let u be the whole bottom, haven't we? But let's see why that's not helpful in this case. Because du would be, what's the derivative of 7? 0 gets rid of that. That's nice. What's the derivative of cosine squared x? What?
You could do the product rule.
I could do the product rule. I could write it as cosine times cosine and do the product rule. Or I could just do the chain rule, right? I bring the 2 down. I leave the cosine alone. And then I take the derivative of the inside. Negative sign. So the issue is, I would have this sign to match with this sign, but then what am I going to do with that cosine? So, integration just got more complicated. In the past, our answer was always u is going to be the bottom. Now that's not going to work. And what you really need to look for when you do u substitution is you want u to be one thing so that when you take the derivative, you get the other thing. And so you were absolutely right the first time. U should be cosine x. And I tried to talk you out of it. You stuck by your guns, sort of. U should be just the cosine x. And then du, the derivative of cosine is negative sine x dx. Which tells me I need a negative sign here to get the negative sign. And then I have to balance it with a minus outside. All right, so this becomes the integral of 1 over 7 plus u squared du, and then that fits into one of our patterns that we have. Oops, I forgot my minus right there. A negative integral, 1 over 7 plus u squared. That's our arctangent formula, that's correct. So we're going to have negative 1 over a. What's a? A is the square root of 7, because remember this number right here is always a squared. So in this case, a squared is 7, which means a is the square root of 7. Arctangent of u over the square root of 7 plus c. Final answer looks like negative 1/7. I'm sorry, negative 1 over square root of 7. Arctangent of cosine over 7 plus c. Well, people said they wanted to do problems where a was not the number 1. So, and I also wanted to do a problem where, I mean, so far, a's have always been integers. We had 16, so we got a 4 before we had a 3, 9 and a 3, so on and so forth.
Could it be like a negative square root of 7 too?
Could a be negative square root of 7? That's a very good question. Anybody got a very good answer?
Can you put negatives into arctangent?
Can you put negative numbers into arctangent? What was our domain for arctangent? Could you put negative numbers into that? Our interval for arctangent, I believe, was negative pi over 2 to pi over 2. So yes, you could put negative numbers into arctangent. So could you use negative square root of 7? Would you get a different answer? The answer is yes, you could use negative square root of 7, and yes, you would get the same answer. Because you need to remember something interesting about the tangent function. The tangent function, and therefore the arctangent function, are something that we call odd. What do we mean by odd functions? What do odd functions do? Nobody remembers odd functions. A function is odd if f of x is odd if when you plug in a negative number, you get the same answer back but with a negative. So example, sine is an odd function. G of x equals sine. Because if I take, for example, the sine of pi over 4, what's the sine of pi over 4? Square root of 2 over 2. And then if I do the sine of negative pi over 4, I get the same answer except it has a negative. So that's negative square root of 2 over 2. So sine is an odd function. It turns out tangent is also an odd function, and therefore arctangent is an odd function. So if I had used negative square root of 7, I'd have a negative there, and then I would have a negative there. But because arctangent is an odd function, I could take this negative sign and I could bring it out front, and when I bring it out front, it would reduce with that negative sign. Negative and negative would make a positive. So that was kind of a long answer to a short question. Could you use negative square root of 7? Yes, you could, and you would have exactly the same answer. And so to make our life easy, we don't. We always pick the positive one. Okay. Nobody had ever asked me that question before. That was a very good question. All right, let's try another one here. Where are the hard ones? I haven't found the hard ones yet. How about the integral? Oh, here's a good one. This is what I was looking for. X minus 3 divided by x squared plus 25 dx. Any good ideas? What's that? Can you be the top? You could be the top. So u would be x minus 3, which means du would just be dx. And then what are you going to do with that x squared down on bottom? But if I'm going to use u to be x plus 3, then I've got to put u's down on bottom.
So, u plus 3.
And then I have u plus 3 quantity squared plus 25. That sounds like it got worse. Instead of just having x squared plus 25 on bottom, I'd have u plus 3 whole thing squared plus 25. That almost seems worse. So could I do that? Yes. I don't think it's helpful. Those are good ideas.
Make u x squared plus 25.
Make u be x squared plus 25, and then what would du be?
2x dx.
2x dx. So what are you going to do with that minus 3?
Solve for x.
But if you solve for x, u is x squared plus 25, you're going to have square roots.
Yeah.
That doesn't sound pretty either. Let me ask you a different question. What if, that minus 3 were not there at all, what would you do? Then I think your u substitution is a good idea. If that 3 were not there at all, u would just be the bottom. Du would be 2x, so we'd need to put a 2 and balance it with a 1/2, and we could do that. Conversely, what if that x were not there at all? Nope. This is, we have a number, and then we have x squared plus 25 on bottom. That's x squared plus a squared. That's our new arctangent formula. But we got them both. So what are we going to do? I'm going to split it into two problems. That's exactly right. I'm going to write this as the integral of x over x squared plus 25 dx minus the integral of 3 over x squared plus 25 dx. So there's a new trick, a trick we've never done before. A fantastic trick. Sometimes you split the integral on the numerator. You split it into two integrals. This one we just talked about. This is the u substitution problem. This one, on the other hand, fits immediately into the arctangent formula. All right, so there's a new trick. You got a new technique you got to look for. Look for splitting the integrals on the numerator. All right, so left-hand side, u equals x squared plus 25. So du is 2x dx. I need to slip in a 2. Balance it with a 1/2. We would have 1/2 the integral of 1 over u du. What's the integral of 1 over u du?
Natural log of u.
That's natural log of u. So we're going to have 1/2 natural log of u, but u is x squared plus 25. So there's the first integral. Minus the second integral, that's going to be 3 on top. And then this one's a straightforward, it fits exactly into our pattern. What's the antiderivative of 1 over x squared plus 25? I'll write it this way. I'll write it in there. That fits into the arctan, where a is the number 5. So we're going to have 3 over 5 arctan x over 5 plus c. Questions on that one? All right, let's try one more for today. How about the integral of x squared plus 3 divided by x times the square root of x squared minus 4 dx. Same deal, split it. Okay. So that's going to be the integral of x squared over x square root of x squared minus 4 dx plus the integral of 3 over x square root of x squared minus 4 dx. Split it on the numerator. First integral, how are you going to do that one? Make the top u? No, I don't think so. First off, reduce an x, right? You got an x there and an x there.
You said x squared minus 4.
U squared, u is x squared minus 4 because the derivative of x squared minus 4 gives you
2x.
that x up on top. So this is the u subproblem. U equals x squared minus 4. Du is 2x dx. Again, I need a 2 there, which means I need a 1/2 there. That becomes 1/2 the integral I'm going to write it this way, u to the negative 1/2 du. Why u to the negative 1/2? Because u to the negative 1/2 is 1 over square root of u. The negative drops it to the bottom. The 1/2 is the square root. I like writing it this way, though, because then I can add 1 to my power, divide by my new power. That's going to be 1/2. U to the 1/2, divide by 1/2. So, in a final answer, when we get all done, we're going to have a square root of x squared minus 4 for the first integral. And then I've got to fill in plus the second one all the way down. Plus the second one, plus c at the end. All right, so how about the second integral? How do you integrate 3 over x times square root of x squared minus 4? That fits exactly into our arc secant. We're going to have that 3 is just going to stay right there. A is the number 2, so we're going to have 3/2. Arc secant, absolute value, x over 2. So I just got to fill that in all the way down here, I guess, the way I wrote it. Arc secant, x over 2 plus c. Arc secant, absolute value, x over 2 plus c. Questions on that?
Plug back in your x, your u's.
Yeah, I did, because I had u here, and then
Oh,
I plugged in my x's over there. Yeah. So I got rid of all my u's. Other questions?
Plug into the fraction.
Oh, 1/2 divided by 1/2. That's the number 1. What about the 3/2? That one just disappeared. So we'll put it back in there. Yes, thank you. That one did just disappear.
Will we ever do definite integrals for like stuff like this or no?
Oh yeah, there's definite integral problems in there.
Definitely.
We'll do that tomorrow.
Okay.
And then also tomorrow we'll do something called completing the square.
Oh.
Whatever that means. All the happy smiles that I see.